Okay, in this tutorial we're looking at section 10.3, which is about solids of revolution. Now this stuff I reckon is really cool. It's one of the better applications of our integration techniques, I believe. Okay, so we'll get straight into it. Okay, so when we look at solids formed by rotating curves about the x-axis, okay, we use the formula v equals pi times the integral from a to b of y squared dx. Okay, so we need a function of y in terms of x only, okay, to be able to do these things. Okay, and if we're looking at solids formed by rotating curves about the y-axis, then it's our volume equals pi times the integral from a to b of x squared dy. And so x needs to be a function of y. Okay, so what we're really doing is we're saying, well, we've got our axis here, and we've got a curve, okay, which is y equals f of x, and we're rotating it this way, okay, around our x-axis. Now I haven't drawn it very well in this example here, okay, because it would be as much above and below the x-axis, okay, and it creates a volume in doing that. Okay, if we're rotating about the y-axis, okay, you can see we're going this way, okay, and A is our lower terminal again, okay, same with here. So they do sort of waffle on a fair bit before they get to those two formulas in the section, but essentially that's all we need. So we'll get stuck into the worked examples. So worked example 5. The area bounded by the curve y equals x squared, okay, the x-axis, the origin in the line x equals 2, is rotated about the x-axis to form a solid of revolution. Find the volume formed. So what we want to do is we want to draw a little picture here so we can get an idea of what's going on. Okay, so we've got that. So we've got our equation y equals x squared. It's going to look something like that-ish. Okay, and it's the area bounded by the curve. Well, that's our curve, the x-axis, that's there. Okay, the origin, okay, so we're here. Okay, and the line at x equals 2. So looking at this area here, it's going to be rotated around this way. Okay, so when it gets rotated, we're going to end up with a volume in there. Okay, so we need to set up our integral. So it's our v equals pi times our integral from 0 to 2, okay, and it's y squared, okay, well y equals x squared, so it's x squared squared, okay, dx, okay, so our volume equals pi times our integral 0 to 2 of x to the 4 dx, okay, so when we do that we get pi times x to the 5 on 5 from 0 to 2. We've got pi outside of 2 to the 5 on 5 minus 0. So that means we've got pi times 32 on 5, okay, which means we get 32 pi on 5, and this would be cubic units. Okay, that's all there is to this one. Okay, so not too bad of a worked example. We'll look at worked example 6. Okay, this one is the area bounded by the curve y equals x squared. Okay, the y-axis, the origin and the line y equals 4. Okay, is rotated about the y-axis to form a solid of revolution. Find the volume formed. Okay, so for this one, again, a little picture can help get our head around what's going on. Okay, so I've got a quadratic again. Okay, and that's between the origin, okay, the y-axis, okay, and the line y equals 4, okay, and it's on this side of it. Okay, although it wouldn't really matter if we thought about it being the other side, because we're going to rotate it around. We're going to end up getting this volume. Okay, so what we need to do is set up our integral again. Okay, so our volume equals pi times our integral. Now this time we're from 0 to 4. Okay, and for this one it's x squared. Okay, well x squared is actually equal to y, and so it's the integral of y dy. Okay, so it worked out quite nicely that we knew what x squared was. They won't always be that nice. Okay, so then we can simply go, well, our volume equals pi times y squared on 2 from 0 to 4. So v equals pi times 16 on 2 take 0, okay, which is simply 8 pi cubic units. Okay, and we're done. Hey, so we've got one last worked example to do, which is worked example 7. So a drinking glass has a base diameter of 5 centimetres, a top diameter of 7 centimetres and a height of 11 centimetres. Find the volume of the glass to the nearest milliliter. So what we've got is a glass that's like this. Okay, so we can say across here is 5, across here is 7, and this height here is 11. Okay, well what we can do is we can actually draw our set of axes here. Okay, and find the equation, okay, of our side here. Okay, and then that way, what we can do then is we can simply rotate that around and we'll be able to work it out. So we need to work out what our coordinates would be here. Well, we've got to be 5 on 2 because we're going to be half of our diameter. Okay, so this point would be 5 on 2, 0. Okay, and this one would be 7 on 2, 11. Up there. Okay, so we can do our rise over our run. Okay, so you can say our m is our rise, which is our y2, which is 11, minus our y1, which is 0, over our x2, which is 7 on 5, minus our x1, which is 7 on 2, which is 5 on 2, okay, which is simply going to be 11 on 1, or just 11. So m is going to be 11. Okay, and then we can set up our equation. So we can say y minus y1 equals m outside of x minus x1. Our equation for a straight line. So we say y minus, we may as well go 0, is 11 x minus our x1, which is 5 on 2. Okay, so we can get y equals 11x minus 55 on 2. Okay, so now we've got our equation there. So we need to set up our integral. So we know that we're going to be rotating around the y-axis. So v equals pi times the integral from a to b of x squared dy. Okay, well we know our a is 0 and we know our b is 11. Okay. Now what we need to do though is actually work out what x equals. Okay, we're going to have to do some rearranging here. Okay, so we of course we make it 11x equals y plus our 55 on 2. So x equals our, sorry, we can probably simplify this a little bit first, make our life a bit easier. Perhaps, yeah, we can make it our 2y plus 55 on 2. Okay, which means we can go, well, x equals 2y plus 55 on 22. Okay, so we can probably again simplify, well, no, we won't need to simplify it anymore actually, so we can just get organised now with our equation. So we can say, well, v equals pi times the integral from 0 to 11 of 2y plus 55 22 squared dy. Well, what we can do, okay, is 22 squared is 484. Okay, so bring 1 on 484 out, because it's just a constant. And say pi on 484 is integral from 0 to 11 of 2y plus 55 dy. Okay, makes it a little bit easier. Okay. So, what we can do then is actually do our integral. Okay, so we'll get y squared plus 55y. Okay, from our, no we won't, sorry, what am I saying? I've forgotten that that is squared. Sorry. So when we integrate, sorry about that, we get our pi on 484, okay, outside of our 2y plus 55 cubed over 6 from 0 to 11. Okay, well what we can do is bring out 6 out and make it pi on 2904, okay, times by, okay, when we put in our 11, okay, we get 77 cubed. Okay, when we put in our 0, we get 55 cubed. Okay. And when we work that out, okay, we get that it's, our volume is about 99.92 pi, okay, which is about, okay, as we know that's pretty much 100, so we end up being at our 314 cubic centimetres. Okay, now the question actually wanted it in millilitres, so we can say therefore volume equals 314 millilitres. Okay. So again, nothing too tricky with this one. Okay, the only difference is we weren't given the equation and we need to work out the equation for ourselves before we could go through and do our actual volume. So look, I don't think you'll have too many dramas with this section. It's just a nice little application of integration really.